Hello grade 12s, my name is Gillian. We are busy with a physical science lesson. Today we're looking at big ideas around electrochemistry, and in particular we're going to zone in onto the electrolytic cell. So electrochemistry is a section that is traditionally not answered very well. And so we're going to really get right into the absolute essentials so that you can answer questions well at the end of the year. So electrochemistry on my board, you'll see, is the main topic. Well, this is the topic name, electrochemistry. Electro meaning it is referring to electrons. Chemistry is about chemical reactions. So the chemical reaction that will give us electrons or free up electrons in order to create electricity is going to be the redox reaction. So in the redox reaction there is a transfer, a swapping of electrons, and so this particular chemistry revolves around redox reactions only. There are two parts of it. The one is the galvanic cell and the other part is the electrolytic cell. So we are going to look generally at the ideas behind these two cells, and then we are going to look at the electrolytic cell in a little bit more detail. So on my board here, the galvanic cell, there are some characteristics of this chemistry that should give you a clue to what we are dealing with. And one of the characteristics is the presence of these electrodes. They are strips of metal that are placed in a solution, and the solution is called an electrolyte. So those solutions there, they are called electrolytes, and these strips of metal called the electrodes are placed in those electrolytes. Another thing that we can see in particular for this galvanic cell is that it has something called a salt bridge. Okay, and I'm drawing a line through that salt bridge. So that is what we call the salt bridge. We will come to that in a later lesson. The other thing to notice here is that there is a galvanometer or a voltmeter, and that is giving us a reading of the potential difference between these two half cells. The half reactions take place in these two beakers. So what that is telling us is that in this galvanic cell, there is a current flowing. Electrons are moving in an external circuit. Let's move on to the electrolytic cell, and we can see here that a similar thing is seen here. We've got electrodes, two electrodes. There is a solution, so there is an electrolyte, but in this case there is an external battery or energy provider, energy source. So that is a really big difference between the galvanic cell and the electrolytic cell. I want to give you an overview of this whole section in writing so we can start processing the chemistry behind it. So if we look at my screen now, it's very busy, I know, but what I've done is I have separated these two cells out and written down what is unique to each one. But we are also going to have a look at what is the same or similar for these two cells. So let's start with the galvanic cell. What defines the galvanic cell is this. It is about the energy and the energy transfer. So the galvanic cell is the cell without the battery or external energy supply. What does that mean? That means that the energy is coming from the chemical reaction. So to define the galvanic cell, it is the electrical potential energy from the reaction that is being transferred into electrical energy. So we have got a flow of electrons. For this to happen, there has to be a spontaneous reaction. So we have spontaneous cell reactions, and when we delve into calculations, we see that when we're finding the EMF of the cell, we've done EMF in electricity, when we're finding the maximum amount of energy that is transferred, we find that that result is positive. So we get an answer which is positive. With the electrolytic cell, it is different. The source of energy has to come from outside the internal circuits, the chemical reaction. It has to be a battery that is put onto the external circuit. And so this is the other way around. The electrolytic cell is the conversion of electrical energy from that battery into chemical potential energy. So it is going to drive the chemical reaction. It drives the chemical reaction. So this cell needs a battery. This is because this reaction is a non-spontaneous reaction. It does not happen without energy being put into it. And we find when we do calculations that the E of the cell is a negative value, and that negative value tells us that this reaction is non-spontaneous and it needs energy to be put in from the outside. What are the things that remain the same? It is definitely, in both cases, definitely based on redox reaction. So we will have a reduction half reaction and we will have an oxidation half reaction. There will definitely be an electrolyte, so a solution that is able to conduct electricity. There will be two electrodes, those strips of metal that are put into the solution into the electrolyte, and one of them is going to be called an anode and the other one is going to be called a cathode. There will also be electrons that flow in the external circuit, whether those electrons are supplied by the chemical reaction in the galvanic cell or whether those electrons are drawn and supplied by the battery in the electrolytic cell. Sure, that's a lot. So let's look at our definitions and what we need to write down. So these definitions are really important because if you have got them learnt, then you can predict and work out which reaction is going to be the oxidation reaction and which reaction is going to be the reduction reaction. So the first thing we do need to know is what is an electrolyte. And there are two options I've given you here. A substance of which the aqueous solution contains ions. So you will remember from the past that if we have a solute that dissolves in a solvent like water, it will dissociate into a positive ion and into a negative ion. Another way of defining an electrolyte is by saying a substance that dissolves in water to give a solution that conducts electricity. Now, you will be asked to define or to say which electrode is the anode and which electrode is the cathode, and it revolves around oxidation and reduction. So what is the anode? Well, the anode is where oxidation takes place. How can we remember that? We can use this trick to help us. An-ox. So think of anode, an-ox. So an-ox is where the oxidation takes place, the reaction where oxidation takes place, and that is the loss of electrons, happens at the electrode called the anode. What about the cathode? So the cathode is where reduction happens. And there's a little trick to remember that, and I've drawn a little red cat. So red cat. So at the cathode, so at the red cat, the cat is cathode, red is reduction. So we can remember reduction happens at the cathode. What about electrolysis? Electrolysis is a process. So here we go. It's a chemical process in which, let's think, we're talking about electrolysis, so that's the electrolytic cell, that's the one with the battery, and so it is a process where electrical energy is transferred to chemical potential energy. Oxidation. How are we going to remember about oxidation? So oxidation is the loss of electrons, and we can use this acronym, oil and Rig. So oil stands for the oxidation. O, oxidation. Oxidation is, that I is, L is loss. So oxidation is the loss of electrons, or the oxidation number is going to increase. Obviously, if electrons are being lost, it's going to become a more positive oxidation number. What about reduction? Well, reduction is the Rig part. So the R stands for reduction, the I stands for is, and the G stands for gain. Gain. So reduction is the gain of electrons. So if something is taking on those electrons, it is going to become more negative, and so the oxidation number is going to decrease. It's going to be a more negative oxidation number. When we speak about oxidation and reduction, often we speak about the substance which is an oxidizing agent and the substance which is a reducing agent. So how are we going to settle that in our minds? So an oxidizing agent is the thing that helps or aids oxidation. And how will it aid oxidation? It would aid oxidation by taking the electrons that are given. So the oxidizing agent is the substance which is actually reduced. The same applies for, or the opposite applies for the reducing agent. What is the reducing agent? The reducing agent is going to aid reduction. It's going to help reduction. And how does it help reduction? It helps by giving the electrons. So it's the substance which is oxidized. A quick reminder, this part of chemistry revolves purely around redox reactions. Redox reactions are reduction and oxidation reactions. It is the transfer of electrons. We've got one substance which gives electrons away, and that is the oxidizing, that is the substance which is oxidized. And we have another substance which takes on those electrons, and that is the substance which is reduced. Grade 12s, it's time for a break. After the break, we will have a look at some examples. Hello grade 12s, welcome back from the break. We are discussing electrochemistry, and right now we're going to look at how electrochemistry is applied. So if you look at my screen, you'll see we've got galvanic cells and electrolytic cells. With the galvanic cells, the application is the wet cell battery, and you find that in batteries that you use in your mouse or in other small electrical appliances, also in your car. And that kind of technology is kind of being transplanted. It's being taken out by more modern technology. The other application for galvanic cells is the standard hydrogen electrode, and that you will need to know, but we're not going to discuss it in this lesson. What I want to look at now is how we apply our knowledge of electrolytic cells to the following, and these are the four areas: electroplating, electrorefining, the chlor-alkali electrolysis, and the decomposition of copper to chloride. Now, electroplating is where we take one metal and we cover it with a very thin layer of an expensive metal, electroplating. Electrorefining is where we take a metal that has got impurities in it, and we try and get those impurities out, and so we get a pure metal at the end. Chlor-alkali electrolysis is, alkali is talking about Na, alkali, the alkali metals. Chlor is chlorine, and so what we do is we make in this, we start off with sodium chloride, which is table salt. You have it on your food every day, and we put it through an electrolysis process, the process of making sodium hydroxide. Okay, so that's an industrial process, and that's part of the applications. So I really don't have time to go through all of them, but what I do want to try and do today is having a look at the decomposition of copper to chloride, and then if we have time, we'll have a look at electroplating. So let's move on to this picture that I have here. So we can see immediately that this is in an electrolytic cell, and the thing that gives it away is the battery, this thing. Because we know that in the electrolytic cell, we need an external energy source, and so electrical energy is being transferred into chemical potential energy. We have electrodes, and I've written a question mark here. What are these electrodes? So these electrodes are made out of graphite. Now, graphite is a kind of carbon, and the graphite is able to conduct electricity. So both of them will be made out of graphite. Why? They just offer a surface on which the half reactions take place. So with our external battery, you can see we've got a negative charge on that side, terminal, and a positive terminal on that side. What is going to happen? Electrons are going to be drawn towards that side of the battery. And so this is going to end up being a positive charge. So this graphite electrode is going to have a positive charge. Electrons are going to be pushed out on this side by the battery, and so this electrode is going to have a negative charge. Hope you can see it there. So there's a buildup of electrons on this electrode. We also have an electrolyte, and the electrolyte is this substance, copper to chloride. So when we have a Roman numeral, copper to chloride, that 2 is referring to the charge on the copper. In water, the copper to chloride is going to dissociate into copper 2 plus ions and the chloride ions. Now there are 2 of them, so it means that for every one copper ion, copper 2 plus ion, there will be 2 negative chloride ions. So I'm going to add this in on the drawing. This is a very simplistic drawing, and I want to give you an idea of what it looks like. So if this is a copper 2 plus ion, then there will be another negative chloride ion. Copper 2 plus on this side, so there will be another chloride ion. Copper 2 plus, there's the one, so there's the other over there. Copper 2 plus, and we'll have a negative and a negative chloride ion. Right, so that's what our electrolyte is looking like. What happens here? Well, if we have a negative electrode, so this electrode that is building up electrons because of the battery forcing electrons or pushing electrons into it, it is going to have an overall charge of negative, and it is going to attract those copper 2 plus ions. And so these copper 2 plus ions will attract, here you can see I've written the name of them, copper 2 plus ions, will be attracted towards this electrode. They will take, each copper 2 plus ion will take 2 electrons and form pure copper. So this electrode on this side, I want to change my color so you can see it. The electrode on this side will start forming not a blue covering, but a slightly like brownish, shiny covering of pure copper. On the other side, this electrode, which is positively charged, is going to attract the negative chloride ion. And those negative chloride ions will donate their electron to the electrode to form a neutral chlorine gas. And we will see bubbles forming on this electrode, and it will be quite smelly. So after a while, if you stick your nose here, which you shouldn't do, if you stick your nose here, you'll smell. It's awful. It's a really unpleasant smell, and it might even burn your nose. So the bubbles, the effervescence tells you that the gas is being formed. And what gas is being formed? Well, it is chlorine gas, which is Cl2. So 2 chloride ions will give away 1 electron each, and they will then form the diatomic chlorine molecule. Let's write these equations down, these half equations down. So we have got, on the one side, we have got copper, 2 plus 2 electrons, forming copper, and it's a solid. You'll see this thin layer of the solid copper being formed. It has an oxidation number of 0, so it's pure copper. What's happening on the other side? The other side is the chloride ion is forming chlorine gas. Okay, so it's a gas. By doing what? It is giving away an electron. But there are 2 of them. Have a look there. There are 2 of them. So we need 2 chloride ions to make the chlorine gas. And so the net number of electrons will be 2 that are given away. Now on this picture, we need to be able to identify which electrode is the anode and which electrode is the cathode. Remember this that we did before the break, an-ox. What does that mean? It means that the anode is where oxidation takes place. How will we know where oxidation is taking place? We need to look at the oxidation numbers of these half reactions. So copper starts off as 2 plus and it ends up as 0. What's happening there? Well, that's not getting more positive. That's not, the oxidation number isn't increasing, it's actually decreasing. So that's not what we're looking for. So let's have a look at the chloride ion and what it does. So the chloride ion starts off as a negative ion, and look what it makes. It makes a neutral, pure chlorine gas. So it is becoming more positive. It's going from a negative oxidation number to a 0, which is more positive. So this is the oxidation reaction, half reaction. So an-ox, the anode, where is the anode? Well, that's going to be over here, because that is where the oxidation half reaction takes place. That means that the other electrode is going to be the cathode. But let's just check. The red cat, that is what we have to say in our heads to remind ourselves reduction happens at the cathode. Which reaction is the reduction reaction? It is this reaction here. We've just worked it out. So copper 2 plus becomes copper solid. It is 0. It's a pure substance. And so that is where, that's the reaction which is the, reduction half reaction. And so this electrode is called the cathode. The cathode. Right. If we look at this picture, we can see that the copper 2+ ions are moving out of solution. They are involved in the reaction that forms pure copper. And so this electrode light, which would have started off pretty blue because the copper 2+ ion has got a blue color, an aqueous solution of it, you'll see it's blue. The blue color is going to become less. It's going to decrease. The copper 2+ ions concentration will decrease because they are busy moving out of solution in this reduction half reaction. Okay. One way of finding these half reactions, because you might be saying, I don't know how to write these half reactions, is to look at this, this table. Now, you might have seen it before. It is the standard potentials table, reduction potentials table, and it is a list of all the reactions that, that we find in our redox reactions. Now, there is a special way that they all are put together. They are put together in degrees of strength. So the one right at the top is going to be the substance that is the strongest reducing agent. And the one at the bottom is going to be the weakest reducing agent. And I'm talking about the 4B table. There are two. I like using the 4B one. This is not the whole one that's on my screen. I've only taken a section so we can see it. But you will see here that here is the copper reaction, the copper 2+ reaction, and here is the chloride ion reaction. So you would have to run your finger down, you'd have to find which ones you are looking for, and then you need to know that when you are reading the reduction reaction, you are reading it from left to right. So for the reduction reaction, which was the copper 2+, you're going to read it from the left to the right. When you are reading the oxidation half reaction, you are going to read it from right to left. And you'll see here, we started off with the chloride ions and we ended up with the chlorine ions. The chlorine molecule. Now, there are two things I want to say before I have to go. The one is, these double arrows are not double arrows. They are telling you that you can read this reaction from left to right and from right to left. So we're not going to write the double arrow when you are writing one of these half reactions. It has to be a single arrow because either one reaction is happening, oxidation, or the other, but both of them can't be happening. So you have to write the half reaction with a single arrow. The other thing that I want to tell you is that depending on where they are in this table, you are going to get a potential difference, and it's called the E0 of the cell. And that tells you whether this reaction is spontaneous or non-spontaneous. And we do it by calculating using that formula. And so we get the value of the potential difference at the anode and the value of the potential difference at the cathode, and we subtract the two. If this is a negative value, it is going to be non-spontaneous. If it is greater than 0, if it is positive, it's going to be a spontaneous a reaction, so or redox reaction. So this particular example that we're doing now for the electrolytic cell, it has to be a non-spontaneous reaction. We have got a battery on the outside in the external circuit, and so its E0 cell value is going to be less than 0. Right, grade 12s, join me for the next lesson. We're doing consolidation. We're going to look at electroplating and some other things if we have time. Good to have you with me today. See you later.